Hello, AB Stat students. I think we're doing a lot better now. We'll see how it goes. Now we're on 6.3, which is binomial and geometric random variables. Okay, I really like this section, so hopefully you guys like it too. So consider the following scenario. You walk into a classroom and are told by the teacher that you need to take a pop quiz over the book you are reading. There's only one problem. You haven't read the book. The quiz consists of 5 multiple choice questions. For each question, there are 4 possible answers. Make a tree diagram to model this chance process. So basically, you're guessing. So basically, you could get your first question right or wrong. Well, there's one question. Then the second question, you can get right or wrong. Then we keep going. So we have our third question. Right, wrong. Sorry, handwriting's hard. Right, wrong. It's hard to write on this. Right, wrong. And we could keep going. Our fourth question, right, wrong. And our fifth question, right, wrong, yada, yada, yada. What's the probability that you get 2 or more correct? Well, we could keep this going and we could count all the branches that make this work, 2 or more. So I'm not going to go ahead and do that because that's too much counting. So we have a binomial probability distribution. You see that word distribution? We've only known about normal distributions up until today. So the binomial distribution is satisfied by these 4 characteristics. Binary, so that means there's only 2 options. And we usually call this success or failure. You guys have heard of binary before, zeros and ones? Well, one would be a success, zero would be a failure, depending on how you look at it. Independent. Each trial does not affect the next. So on that last one, you could either get the question right or wrong. And if you get the first question right, that doesn't mean you'll get the second question right or wrong. Doesn't affect it at all. There are a set number of trials. So we had 5 trials. Okay, that one doesn't need any explanation. And the same probability of a success each time. On that last one, there's a 25% chance because remember there was 4 options. There's a 25% chance that you got it right and a 75% chance that you got it wrong, right? Because 1 out of 4, 3 out of 4. So the probability of success does not change. Here are 2 scenarios involving chance behavior. In each case, determine whether the given random variable has a binomial distribution and justify. So genetics says that children receive genes from each of their parents independently. Well, there's one of our conditions. Each child of a particular pair of parents has a probability of 0.2 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood. This is exactly the same sort of situation. They either have type O blood or not, so it satisfies the binary condition. It was independent, like we said. There are 5 children, so 5 number of trials is 5, and the same probability of success. Each child has a 0.25 chance of having type O blood. So that's exactly like our last one. So you could write all that. I'm not going to right now. Shuffle a deck of cards. Turn over the first 10 cards one at a time. Let Y equal the number of aces you observe. Well, our binary condition would be an ace or not. So it works for that one. Our independence would be each trial not affecting the other. Well, if we have an ace in the first card, that lowers our chance of having an ace for the second card. So these are not independent. Let's keep going. The number of trials, is there the same number of trials? Well, there's 10 cards. Is there a set number of trials? Yes, there's 10 cards, so 10 trials. So it meets that one. And S, the same probability of success for each trial. Well, that is the independence thing, so no. So you like my little acronym BINS? This is binary, independent, number of trials, and same probability of success. Each child of a particular pair of parents has a probability of 0.25 of having type O blood. We already talked about this. Genetics says that children receive genes from each of their parents independently. If these parents have 5 children, the count X of number of children with type O blood is a binomial random variable with N equals 5 trials and a probability P of 0.25 of a success on each trial. In this setting, a child with type O blood is a success, and the child with another type of blood is a failure. What is the probability X equals 0? That is, what's the probability that none of the 5 children has type O blood? It's the chance that all 5 children don't have type O blood. The probability that any one of this couple's children doesn't have type O blood is 1 minus 0.25. Remember that complement rule? By the multiplication rule for independent events, we know that we have a failure, another failure with the second child of having type O blood, failure, failure, failure. Now, if we think back to our original tree diagram, the wrong, 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 wrong only happens one time. There's only one way to do that. If I wanted to use some algebra to clean this up, I could say 0.75 to the 5th power. Now I'll go to my calculator. 0.237. So 23.7% chance that none of the children have type O blood. That's not too bad. How about the probability that X equals 1? Okay, so there are several different ways in which exactly one of the 5 children could have type O blood. For instance, the first child might have type O blood, while the remaining 4 children don't have type O blood. The probability that this happens is we have a success of type O blood and then failure, 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 failure. So we have 1 success and 4 failures. So this is 0.25 times 0.75 to the 4th power, right, for 4 failures, because it's 0.75, 7 times 0.75 times 0.75 times 0.75. But this can happen in multiple different ways. Let's go back up to our tree diagram. We could have 1 success and then failure, 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 failure. That's one way of doing it. Then we'd have to go to this branch because that's the only way that would happen over here. We could have 1 failure, then success, and then failure, failure, failure. Then we could have failure, failure, success, failure, failure. So let me write those all out. So we could have like success, failure, failure, failure. We could also have had failure, success, failure, 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 success, failure, 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 success, failure, and failure, 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 success. There are 5 different ways we could have one of the 5 children having type O blood. So we multiply this whole thing times 5. So the probability that X equals 1 is 0.395. So I'm going to say 396. Find the probability that exactly 3 of the children have type O blood. Well, this is where we have to do that counting again. So you have to figure it out how many different ways we could do this. So we have some new notation that could tell us how to do it. I'm not going to show you how to do that binomial stuff too much, but we're going to use our calculator to find these probabilities. It's important to state the right information. So we need to state the name of the distribution, which is binomial in this case, the parameters, which is the number of trials, and the probability, so n and p. And then we need to write a probability statement like this. So I'm going to go back through and do all of these. Probability X equals 0. So menu, statistics, distributions, and this is where we have the PDF, CDF. So we're going to start with a binomial PDF. This is probability distribution function. So we have the number of trials. We have 5 trials. The probability of success is 0.25, and we wanted to know where we get 0 successes. So this is 0.237, which matches. Then we're going to use PDF again. But this time we have 5 trials. Our probability of success is the same. This time we want to know where exactly one of the children, 0.3955, also exactly the same. So things that we need that we're missing, we needed to say this is binomial. N equals 5, P equals 0.25. Okay, and we say that for all of them. I have my probability statement needs to be probability x equals 0. And this one, we have x equals 1, binomial, same thing. The probability that exactly 3 of the children have type O blood. So binomial, and we want to know the probability that x equals 3. Same thing. .088. Okay, if we say those 3 things, the distribution, the parameters, and the probability statement in our answer, so 4 things really. Should the parents be surprised if more than 3 of their children have type O blood? So this would be a little different. This probability statement would be x greater than 3, more than 3. So this is the probability x equals 4 plus the probability x equals 5. So we could do that. We're going to use that PDF. So I'm going to copy this. This is x equal to 4 and 5. So 0.01 plus 0.0000 that. So I get 0.0156. You see how I added them together? I had this one and I had this one, and I added them in my calculator, so I didn't write it all out. That is binomial PDF. So this is where you need to make a huge note somewhere. PDF is for equals sign, and CDF is for our inequality symbols. Okay? CDF stands for cumulative distribution function. This is probability distribution function. This is cumulative distribution function, which makes sense because you're accumulating more than one. So let's go do this as a CDF to make sure we get the same answer. So menu, statistics, distributions, binomial CDF. We still have 5 trials. Our probability of success is still 0.25. We're going from 4 trials to 5 trials. And there's the exact same answer. So it works. So CDF is using these included symbols. So really a better way of saying this might be the probability that x is greater than or equal to 4. Greater than or equal to 4, because we want to use these inclusive symbols. If a count x has the binomial distribution with the number of trials n and the probability of success p, the mean and standard deviation of x are, well, there's mu, n times p, and the standard deviation, square root of np, 1 minus np. This is all something that you'll have on your formula sheet, so you don't even have to memorize it. So here's an example. The manager of a food market guarantees that none of his cartons of a dozen eggs will contain more than 1 bad egg. If a carton contains more than 1 bad egg, he will replace the whole dozen and allow the customers to keep the original eggs. If the probability that an individual egg is bad is 0.05, how many eggs would you expect to be bad? right? Expected value is the same thing as mean. So we have 12 eggs per carton, and the probability of a success is a bad egg. Success doesn't necessarily mean good things, so it's just 12. So mu is 12 times 0.05. So we expect 0.6, not even a whole egg, to be bad in each carton. What's the probability that the manager will have to replace a given carton of eggs? So if there's more than one bad egg, he will replace the whole carton. So we want to know the probability that x is greater than or equal to 2. Remember, this is the same thing as saying x is greater than 1. So we need to use the binomial CDF. This is a binomial distribution. There's n and p. So the number of trials is 12. Probability of success is 0.05. We're going from 2 to 12. 0.118. A music distributor inspects an SRS of 10 CDs from a shipment of 10,000 music CDs. Suppose that, unknown to the distributor, 10% of the CDs in the shipment have defective copy protection schemes that will harm personal computers. Count the number X of bad CDs in the sample. Are the conditions for a binomial setting met? Well, let's check it. We have binary situation, either they're defective or not. So that's met. We have independence. Each CD is independent of the other one. We can assume that. N is 10 because there's 10 CDs from that shipment of 10,000. And our same probability every time, yes, P equals 0.10. Find the probability using the binomial distribution. So we want to know the probability that there will be any bad CDs. So the probability X equals 0. This probability that there won't be any bad CDs. I said it's binomial, I said N and P, so that's good enough. 0.348. I'll round that to 349. Find the probability by multiplying probabilities. Well, remember we said 0, so we could have also said 0.10 times 10. When taking an SRS of size n from a population of size big N, this is population n, I guess. Sometimes they do that, that's rare. We can use a binomial distribution to model the count of successes in the same as long as n is less than a tenth of the size. Okay, so 10 is less than or equal to 1/10 of 10,000, and that's going to work. Suppose that a count X has the binomial distribution with n trials and a success probability P. When n is large, the distribution of X is approximately normal with the mean and the standard deviation. Remember those formulas? As a rule of thumb, we'll use the normal approximation when n is so large that np is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So we'll use the normal approximation. So sample surveys show that fewer people enjoy shopping than in the past. The survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. The population that the poll wants to draw conclusions is all U.S. residents aged 18 and over. Suppose that exactly 60% of all U.S. adult residents would say agree if asked the same question. So this is that population. X is the number in the sample who agree. Show that X is approximately a binomial random variable. Well, we have the binary, they either agree or not. Independent, we can assume that each person, their conclusion is different and not affected by anyone else. The number of trials is 2,500, which is huge, and the probability of success, P, is 0.6. So yes, that works. Check the conditions for using a normal approximation in this setting. We want our sample is less than 1/10 of the population. So is 2,500 less than or equal to 1/10 of all adults 18 and over? Well, that's for sure. Don't even have to calculate it. That's good enough. And the other one, we need to check that NP and N times 1 minus P are greater than or equal to 10. And they're totally going to 2,500 times 0.6 and 2,500 times 1 minus 0.6, which is 0.4, are going to be greater than or equal to 10. We'll check that real quick. Totally fine. Use a normal distribution to estimate the probability that 1,520 or more in the sample agree. So we want the probability that X is greater than 1,520. So mu of X is N times P, which was 1,500, right? From right here. And sigma of X is the NP 1 minus P all square rooted. (24.49). And we want to know the probability that X is greater than 1520. So here we have that normal PDF and normal CDF. Well, we've been using CDF the entire time because it's cumulative distribution function. We are always saying greater than or less than, or even in between. We never had X equals anything because we never had a discrete normal variable, and we won't in this course. That's why we use CDF. Point 2.1. So even though it's been a long time so far and we've just done binomial, the geometric is very, very, very similar. What if we don't have a set number of trials, but rather we count the number of trials necessary to achieve success? The conditions are similar to that of a binomial random variable. So we still have that binary condition, we still have the independent. This we're going to call T for trials until your first success. So B-I-T-S. So the only thing different is we don't have a set number of trials. So this is what it looks like. If y is a geometric random variable with the probability of success p on each trial, then its mean expected value is 1 over p. Think about this. If you have a coin that you're flipping and you're trying to figure out how many times it takes you to flip your coin until you have your first success that you would expect, well, the probability of flipping a heads is 1/2. So if we said 1 over 1/2, well, using our algebra, we could multiply the top and the bottom by 2 and get 2 over 1. So 2. It would take approximately 2. If you think about rolling a die, the probability of a success of rolling a 6, well, the probability of success is 1/6. So we take the reciprocal. It would take us an expected 6 die rolls until we get a first success. That is, the expected number of trials required to get the first success is 1 over p. Suppose you roll a pair of fair 6-sided dice until you get doubles. Let t equal the number of rolls it takes. Show that t is a geometric random variable. So we're trying to roll until you get doubles. So we have either doubles or not, so the binary works. Each die roll is independent, has no memory of a previous trial. We do not have a number of trials, but we want to know the trials until we get doubles. So trials until first success. And the probability of rolling doubles is the same every time. How many rolls would you expect to get doubles? Well, we need that probability of success. Well, doubles would be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So there's 6 ways to get it. Out of all ways, we could roll 36 die. So this is 1 out of 6. We've talked about that 36 before, so that's why I'm going quick. So we would expect 6 rolls, right? That 1 over p, and then we multiply the top and the bottom by 6. We can because that's a 1. That cancels this, and we get 6 over 1, 6. Find probability t equals 3 and interpret this result in context. So on our calculator, we're going to use a geometric. There's our distribution name. We need our parameters. The only parameter on this one is 1/6. And there's our probability statement. They already did it for you. Since it's equals, we're going to use PDF. So a geometric PDF, I can put 1/6 in there, and I want 3 rolls. 0.1157, so let's say 0.12. So we interpret this result. In the long run, there is a 12% chance that it would take us 3 die rolls until we get doubles. So that would mean we would have a failure, and then we would get our doubles. In the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability this happens. Well, that's really similar. We would have all the same stuff, except we want the probability within 3 turns. So the probability x is less than or equal to 3. So this is a CDF. Now we can't have 0 trials. We have to be able to roll at least once. 0 to 3. 0.42. A professional soccer player succeeds in scoring a goal on 84% of his penalty kicks. Assume that the success of each kick is independent. In a series of games, what is the probability that the first time he fails to score a goal is on his 5th penalty kick? So that means he makes, and then misses. I'm going to call that a failure. So this is a little different. This is kind of backwards. If we say trials until our first success, really we're saying failure, 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 success. Even though we defined a success as scoring, a success in this case is missing. So we could do this by pretty easily without the calculator. We could say, so if he makes it, it's 0.84, then he makes it again, then he makes it again, then he makes it again, and then on his 5th one, he finally misses. Okay, and we can simplify this to 0.84 to the 4th times 0.16. 0.0796, I'm going to round that 0.08. Now you can do it this way. On the AP test, there was a question like this in 2016, and a lot of people didn't do this for some reason. You can also use your calculator. This is the probability that he misses is on his 5th trial. So it's a geometric PDF. So the missing is the success technically, because it's the trials until your first success. There it is, the exact same thing. What's the probability he scores on 5 or fewer of his next 10 penalty kicks? Well, since there's 10 penalty kicks, Now we're at a binomial again. So we are doing binomial with 10 trials, and we want to know the probability he scores on 5 or less. So let's say scoring is a success, so 0.84, and we want to know the probability he scores on 5 or less. So this is a CDF. .01. Suppose that our soccer player is out of action with an injury for several weeks. When he returns, he only scores on 5 of his next 10 penalty kicks. Is this evidence that his success is now less than 84%? And we explain. This is 5 or less, so it's even less. This is the probability that x equals 5, and this is even higher than that. So since this is really, really, really unlikely, 0.01, we would probably say that this is evidence against his 0.84 probability that he would score. So that injury probably did affect him.